Now we want to illustrate Cramer's rule for a system of three equations. Consider the following system. X plus y plus z is 0, 2x minus y is 1, and x minus y minus z is 0. First we compute the determinant of the system, which is the determinant of the matrix 1, 1, 1, 2, minus 1, 0, and 1, minus 1, minus 1. We can use the Cyrus rule, so we evaluate the product of the entries on the principal diagonal, which is 1, and then on the neighboring diagonals, 1 times 0 times 1 is 0, and finally 1 times 2 times minus 1 is minus 2, and we subtract the products along the diagonals perpendicular to this one. 1 times minus 1 times 1 is minus 1, 0 times minus 1 times 1 is 0, and minus 1 times 2 is minus 2. So we have, this is 3, plus 1 is 4, plus 2 is 2. What is important that this is different from 0. And then we have 3 unknowns, so we compute 3 more determinants, and that will be determinants of a matrix like that, where the first or the second or the third column is replaced with the right hand side 0, 1, 0. So let's denote it D1, where we use the right hand side column on position 1. That means 0, 1, 0. And we copy the rest, namely 1, minus 1, minus 1, and 1, 0, minus 1. And this determinant is easy to compute by expanding along the first column. So we have minus times determinant of what remains if we delete the first column and the second row. That means the determinant 1, 1, minus 1, minus 1. But you see that the columns are the same, they are linearly dependent, so the determinant is, yes, 0. Otherwise you could write minus 1, plus 1. In a similar way, we compute the second determinant, or corresponding to the second variable. We copy the first column, 1, 2, 1. We replace the second column with the right hand side, 0, 1, 0. And we copy the last column, 1, 0, minus 1. Now we again expand this determinant along the second column. So we have 0, 1 times the determinant when we delete the second row and the second column. So this is 1, 1, 1, minus 1. And the result is minus 1, which is minus 2. And to get z, we evaluate the third determinant when we use the first column, 1, 2, 1. We use the second column, 1, minus 1, and we replace the third column with the right side column, 0, 1, 0. And this determinant is plus, minus. And when we delete the second row and the third column, we get the determinant 1, 1, 1, minus 1, which is minus 1 is minus 2, times minus 1 is plus 2. Well, and now we can use these determinants to write the unknowns. X is d1 divided by d, which is 0 divided by 2, which is 0. And similarly, from d2, we can find y, namely d2 divided by d, which is minus 2 divided by 2, which is minus 1. And z is d3 divided by d, which is 2 divided by 2, which is 1. So this is the solution. We can check this solution easily. On the left of the first equation, we have x plus y plus z, which is 0 minus 1 plus 1 is 0. And this is exactly what we have on the right. On the left hand side of the second equation, we have 2x minus y, which is 0 minus minus 1, which is plus 1, which is exactly what we have on the right. And on the left of that third equation, we have x minus y minus z, which is 0, minus 1 is plus 1, minus y is plus 1, and minus z is again 0. It was good. This approach has one advantage. When we have a square system and the determinant is different from 0, then we are sure the solution exists and is unique. And then, say for a large system of 50 unknowns, imagine that we are interested in x3 only. And we don't care about the values of the other unknowns. So then we evaluate d and d3, and that gives us the third unknown, and we don't have to evaluate the remaining unknowns if they are not important for us. Well, and in the next section I will give you some reasoning, some proof why this works.